Good morning, everyone. My name is Mason McFarland. I'm currently a rising junior at Gettysburg College, and today I'll be talking about synthesis and characterization of potential superconductive materials. This summer, I had a chance to work in the predictive materials lab alongside Dr. Benjamin, and there I learned how to learn predictive techniques regarding superconductivity in compounds with the emphasis on research, synthesis, and characterization. For those of you who don't know, a superconductor is a material that conducts electricity with zero resistance. We can see examples of superconductivity in the medical field, like an MRI machine, in the tech field, like a quantum computer, and in the transportation field, like magnetic levitation trains. Our goal in this research is to discover new superconductive materials that will improve the efficiency of electrical devices, but also advance research towards room temperature superconductivity. As you see in the bottom right, we see a resistivity to temperature graph. This graph is an ideal data of what superconductivity looks like. As we see the temperature drop, so does the resistance until it sharply reaches zero. Now, how do we get started with this project? After we do research on the compounds that we want, we head over to step one, designing the quartz tubes. Using a hydrogen torch, we shape the quartz tubes and put elements inside of them and seal the quartz tubes. After we're done sealing them, we move over to the synthesis process where we make our crystals. In the synthesis process, we program a box furnace, and our synthesis techniques are chemical vapor transport, flux growth, and partial solid state reaction. Now that we made our crystals, we'll move over to step 3, which is the sample prep for characterization. In this step, we will put 4 gold wires on our crystal using silver paste as glue and attach these wires to a stage. Now that the stage is set, we'll move over to the final step, which is characterization, which we will then put the samples in a 16 Tesla magnet and read the magnetoresistance and zero field resistance using the physical property measurement system. Here are the results, starting with the ones that we made. We made a total of 8 compounds. Some need to be resynthesized because during the synthesis process, the quartz tubes broke, so we'll have to just resynthesize those. Some made it past the synthesis process but need to be measured, and some needs to be remeasured because as you see in figure 10, that although it has promise for superconductivity, it has a lot of noise. We also had a chance to work with users, and we measured a total of 6 of their samples, and we have an example on figure 11 of one of their samples. In conclusion, out of 20 compounds considered in our research, only 14 were chosen. Out of 14 chosen, synthesis was attempted on 8, and out of the 8 attempted, only 1 had a potential to be a superconductor, which was shown in the previous slide. These past 10 weeks, I learned a lot, and I have learned many techniques and topics, and I feel like the one that I enjoyed the most was the 3 synthesis techniques. Also, with these 10 weeks, I can see a lot of improvements that could have been made, and one that I'd like to highlight is my sample preparation techniques. An example of that would be, for instance, when I started, it took about probably 4 or 5 hours for me to put on wires on a sample, versus now it's probably 30 minutes. And I would like to see either the time cuts down or even a more quality, accurate wire attachment so that the measurements could be more accurate. Overall, I had a great time. I learned a lot, and I'd like to thank Dr. Charmaine Benjamin for helping me throughout this project. Thank you.